This is Pete Johnson from Cyphos Technologies. During the next few minutes, I'd like to introduce an innovative new test capability available to manufacturers of Ethernet products with one or more 10-100 1000 base T interfaces. The PhyView analyzer from Cyphos Technologies is the world's only plug-and-play true physical layer test of 10-100 1000 base T Ethernet. To start this presentation, we will take a look at the existing and well-established paradigm for 10-100 1000 base T interface testing. We will then introduce a new paradigm that is uniquely enabled by the PhyView analyzer from Cyphos Technologies. We will then explore PhyView analyzer applications. Following that, we will get into some detail concerning PhyView analyzer transmitter and interface testing, and then cover the topic of receiver testing with the PhyView analyzer. That will be followed by an introduction of the Phi Performance Test Suite, the most automated solution for 10-100 1000 Phi testing ever conceived. We will touch on PhyView analyzer software and accessories. We will then wrap up by once again considering how the PhyView analyzer will cause you to rethink Ethernet testing. The traditional paradigm affecting 10-100 1000 base T Ethernet testing is readily segmented into three test strategies. Traditional Phi parametric test consists of methods that are dictated by IEEE 802.3 standards. This testing is designed to assure interface interoperability over all connection environments. An emphasis on transmitter measurements assures high defect coverage in the areas of transmitter and interface characteristics. The prevalence of time-domain baseband measurements has led to the formation of commercial tools from well-known oscilloscope manufacturers such as Tech, Agilent, and LaCroix. In addition, testing laboratories such as UNH-IOL offer formal services for IEEE 802.3 compliance testing. A second strategy in common use is packet flow testing. This testing is typically easy to set up and simpler to automate than traditional Phi parametric testing. Commercial packet generation and analysis equipment is abundant and often geared to testing multiple Ethernet ports. Low-cost methods that avoid expensive test instrumentation have also been routinely deployed. A third strategy involves either a crude link go-no-go test or simply no testing at all. This minimal cost strategy relies on the maturity of technologies and the inherent capabilities of the Ethernet network connections to hide lower-level defects. It also benefits from average customer acceptance of defects. For example, when users simply shift a physical connection from a defective Ethernet switch port to an unused port. Looking closer at traditional IEEE 802.3 test methods, it quickly becomes clear that these measurements involve considerable investment in test equipment such as high-speed, high-bandwidth digital scopes, specialized test fixtures and probes, specialized software, as well as instrumentation for vector network analysis, test signal generation, and packet flow generation and analysis. Equipment costs can readily exceed $100,000 to test a 10-100 1000 base T interface. Test labs offer services to test several ports a year for between $10,000 and $35,000. Secondly, there is nothing fast or easy about these measurements. Measurements typically address one Ethernet transmission wire pair at a time. A 24-port gigabit Ethernet switch with an auto MDI feature presents 24 10 base T pairs, 48 100 base TX pairs, and 96,000 base T pairs for testing. There is virtually nothing in common between these transmission technologies, so the full coverage of this 24-port switch consists of a series of measurements on 168 transmitting pairs. Time domain measurements are challenging to automate and are very susceptible to probing characteristics and triggering issues. Additionally, most 1000 base T measurements require special test modes of the Phi silicon that are only accessed by poking registers in those devices. These methods also require high expertise. Knowledge of IEEE 802.3 specifications and test methods is essential. Implementing and properly characterizing fixtures and probes is vital to measurement integrity. Additionally, there is a need to control silicon chip level test modes. IEEE 802.3 specifications are typically vague or non-existent in descriptions of receiver measurements and testing. The heavy focus is on transmitter testing. Bit error rate specifications in 802.3 specs for 10 base T and 1000 base T are not directly measurable since the lowest data entity in Ethernet is a packet. All of these issues combine to assure that traditional PHY testing is done only at very low sample rate. Often, testing is restricted to one pair of one port with the assumption that those measurements are indicative of all other pairs and ports. Packet flow testing should not be confused with physical layer testing. Packet flow test is functional in nature, but it is not parametric. It does not answer how good or how bad, nor does it answer where, when there is in fact a defect. In truth, packet loss magnitude is both a function of defect type and of defect magnitude, a fact that assures that the defect nature will be hidden to packet flow testing. From a physical interface perspective, packet flow testing typically suffers from vague test conditions. Test ports and connecting cables utilized might be considered known good, but are not formally characterized and are seldom characterized at all. The absence of a controlled link impairments further blurs the significance of zero packet loss measurements. For those interested in bit error rate measurements, the connection between measurable packet error and unmeasurable bit error is loose and situation dependent. The minimum effective packet size in 100 and 1000 base T is 640 bits, thus producing an uncertainty of 640 per packet drop as to what the actual bit error count is. In 1000 base T, forward error correction built into the physical layer further obscures bit error rate performance. Finally, packet flow testing is normally associated with multi-port devices such as Ethernet switches where packet streams can be bridged from a receiving port to a separate outgoing port and back to the packet analyzer. A crude link test, or no testing, as a strategy is easy to rationalize in many cases. Traditional PHY testing, and perhaps even packet flow testing, may be considered too costly and too laborious. Silicon and component suppliers will attempt to differentiate their products by saying that testing is unnecessary. Link-up testing, that is, just linking two ports with a short patch cable, is simple to do and may typically produce a very high yield. Price competition restricts investments in quality and reliability, and customers, particularly those purchasing low-price equipment or multi-port devices, are more likely to tolerate defects. In truth, equipment suppliers should consider some factors before arriving at this strategy. First, is the device largely implemented as a single component, such as an Ethernet switch on a chip, or does the design involve many discrete components, such as individual PHY devices per port? In general, more components increases risk of defects. What is the typical usage of the Ethernet device? If it never sees more than 10 meters of link distance, it will be immune to problems that might appear when links run between 60 and 100 or more meters. What kind of environment does the device typically experience? A small office might not have much in the way of ambient noise sources, dense cable runs, and extensive patch panels that all offer the opportunity to impair electric signals. Conversely, larger manufacturing and office facilities represent a more demanding performance environment. Other considerations are application and expectation driven. A standard computer link used for web access and file transfer is much more tolerant application than a PoE-powered wireless access point or audio system installed in the presence of high-density fluorescent lighting. In applications such as manufacturing sensors and controls or aerospace link-ups, there will be expectations of high reliability in the Ethernet interface. The bottom line is that successful link test is not a measure of performance and could never assure performance over all of the applications, environments, and conditions under which 10, 100, 1000 base T links are intended to operate. Let's summarize the 10, 100, 1000 base T test paradigm graphically, plotting defect coverage and sample size. Traditional Ethernet PHY testing would certainly represent high defect coverage, particularly in the areas of transmission and interface testing. However, sample size is necessarily low because of the laborious nature of these tests. Packet flow test spans a relatively wider range on both axes, with defect coverage dependent on length of packet flows and the degree of characterization of entities such as known good test ports and patch cables. However, defect coverage is well short of traditional Phi testing, while sampling can realistically range all the way up to 100% of produced Ethernet ports. Link test is well suited for high sample coverage but offers very limited benefit on the defect coverage dimension. This leaves a relatively large region we might describe as the 10-100-1000 coverage gap, where high defect coverage and high sample rates would intersect. The PhyView analyzer from Siphos Technologies fundamentally alters this paradigm. To begin, the PhyView analyzer produces true parametric physical layer measurements. This means that testing will address physical layer performance, assess interoperability robustness, and will localize defects. The PhyView analyzer is a true plug-and-play, with each test port directly interfacing to the device under test through RJ45 test cables and without the need for adaptive fixtures and silicon-based test modes. The PhyView analyzer will test any 10-100-1000 port anywhere, anytime. 10-100-1000 physical layer testing is truly automated to the extent that all of the testing of all pairs on multiple ports can be accomplished with a single button press. Automatic pop-up spreadsheet reports graphically depict physical layer performance with color-coded assessments ranging from excellent to marginal to failing. Users do not need expertise in 802.3 specifications or test methods. The PhyView analyzer will fully test standalone Ethernet ports or can automatically sequence up to 24 ports, that is 96 gigabit Ethernet pairs in a single report. Especially unique is the degree and efficiency of Ethernet port receiver defect coverage offered by the PhyView analyzer. Each PhyView test port combines precise, versatile link impairments with link monitoring or packet flow measurements to rapidly evaluate receiver performance. Before taking a closer look at the capabilities of the PhyView analyzer, let's briefly review some typical applications and test configurations. Testing a 24-port Ethernet switch is as simple as connecting one test lead, one patch cable, per port between the device under test and the PhyView analyzer. For low port count testing, the compact PhyView analyzer offers 2 test ports and a portable instrument package. The PhyView analyzer can also assess quality of physical layer performance at any service outlet, thereby appraising the combined performance of the Ethernet link partner and the media between the device and the service outlet. Each PhyView analyzer test port can be combined with an external packet analyzer to perform more sophisticated packet metric measurements that include many of the controlled channel impairment capabilities of the PhyView analyzer. This further extends its already robust receiver testing capabilities. The PhyView analyzer can also be utilized as a 2-port test instrument to make measurements on both passive and active link components. Finally, the PhyView analyzer, combined with the PowerSync analyzer from Siphos Technologies, provides a fully automated solution to the extremely tricky challenge of assessing the impact of various DC unbalance levels on Ethernet power sourcing equipment, or PSEs. We'll now move on to a review of the PhyView analyzer measurements and metrology. Most PhyView analyzer measurements are performed while the test port is physically and logically linked to the 10-100-1000 port under test. Each test port has full capability to control link conditions such as link rate, duplex, connection polarity, and master-slave roles. Similarly, each test port has capability to report on actual link configurations and link status. Results from auto-negotiation with a link partner will also be reported. The PhyView analyzer offers 4 transmission measurements: power spectral distortion, residual distortion, wideband transmit power, and pair timing skew. The PhyView analyzer also offers 2 interface measurements: wideband return loss and wideband crosstalk. For receiver test metering, The PhyView analyzer offers a link stability meter and a layer 2 or MAC frame generator and counter capability. As mentioned earlier, these will combine with a robust suite of physical impairments to compose effective and efficient receiver tests. Each of these measurements will be further explained in the coming slides. Every PhyView analyzer port offers a full range of link configurations that can be used to force ports under test into desired link modes. These include link rate, connection mode, duplex mode, and gigabit timing mode. Additionally, test ports can be configured to output Ethernet test signals, including gigabit signals 1 through 4 and 100 base T idle signal. Link status reports the active link configuration and state. Configuration includes link rate, connection mode, duplex mode, and gigabit timing mode. Link state indicates the current link condition, that is, linked or unlinked, and link record reports history of link status since the previous measurement, whereby one or more link drops will report as dropped. Link configuration and link state are vital tools that support all other physical layer measurement functions. The PhyView analyzer can also report link partner capabilities that are acquired during auto negotiation prior to link up. These include port under test rates, duplex modes, and gigabit timing modes. Auto MDI or connection mode flexibility is also reported. Power spectral distortion, or PSD, is one measurement that points out a major difference between the PhyView analyzer and traditional 10, 100, 1000 base T Phi testing. The PhyView analyzer generally measures signal power levels, including power over frequency, rather than measuring voltages in the time domain. PSD, more specifically, is a measure of the difference between an ideal transmitted power spectrum and an actual measured transmitted power spectrum. The ideal transmitted power spectrum of a 100 base TX or 1000 base T transmitter would be the power over frequency graph from a perfectly nominal, mid-specification, middle-of-the-mask transmission signal. The PSD measurement that can be configured to user-selected frequency spans anywhere between 20 kilohertz and 100 megahertz. Power over frequency is reported as dB nominal, where 0 dB equates to an ideal transmitter, while positive values correspond to overpower and negative values correspond to underpower performance. Power spectral distortion is sensitive to several characteristics of transmitted 100 base TX or 1000 base T signals. Different output level, or peak-to-peak voltage, affects power measured in the low megahertz regions. Slew rate, or rise-fall time, affects power at frequencies above 60 megahertz. Droop, or baseline wander, affects power at very low frequencies below 200 kilohertz. Defects in magnetics and connectors can result in power excursions in any frequency band depending on the nature of the defect. PSD is measured on transmit pairs 1, 2, 3, and/or 4. The measurement offers a dynamic range between minus 30 dB nominal and plus 3 dB nominal. When testing Ethernet ports, most measurements and test limits will be in the vicinity of 0 dB. However, in a two-port test configuration, PSD can readily be utilized to measure 4-pair insertion loss of a 100-meter spool of cable. The PSD measurement can run concurrently on multiple test ports. The meter is locally calibrated, much like calibrating a vector network analyzer for an insertion loss measurement. Local calibration is performed between test ports 1 and 2 on each test blade and is utilized by PSD, return loss, and crosstalk measurements. Residual distortion, or SNR, is a measurement of non-predictable, non-correctable distortion within an incoming signal from a 100 base TX or 1000 base T transmitter. More specifically, it is the deviation from ideal signal characteristics after compensation for expected imperfections such as attenuation, linear phase shift, gigabit echo, and gigabit near-end crosstalk. Common causes of residual distortion would include alien crosstalk or amplitude noise ingress, signal clipping or compression, severe wideband attenuation, nonlinear filtering, and excessive phase noise or jitter. SNR is a vital, direct, and time-efficient predictor of theoretical bit error rate. That is because any form of signal distortion that a receiver cannot correct for will ultimately flow through into the binary discrimination mechanisms. SNR is reported in dB with a measurement range from about 17 dB to 36 dB, where higher is better. 36 dB corresponds to 1 part signal distortion in 4,000 parts, or 0.03%. SNR can be measured on pairs 1, 2, 3, and/or 4, and like PSD, can be done concurrently on multiple ports. As will be seen later, the PhyView analyzer utilizes SNR measurements as a check and balance during impaired receiver tests to assure applied impairments do not disrupt test port receiver performance. Wideband transmit power is a measure of the total incoming signal power on a transmitting pair. More specifically, it reports the difference between ideal and measured wideband transmitted power. This meter is factory calibrated to perfectly nominal, mid-specification, middle of the mask 100 base TX and 1000 base T transmission signals. Like PSD, it reports in dB nominal, where 0 dB indicates nominal power level, positive values indicate overpower, and negative values indicate underpower. The measurement has a range from roughly minus 15 dB to plus 3 dB and is performed on pairs 1, 2, 3, and/or 4. Pair timing skew is a 1000 base T measurement that measures the gigabit symbol resolution or 8 nanosecond time skew between 4 transmitting pairs. This measurement offers a range of 0 to 80 nanoseconds and is always referenced to one of the 4 pairs. The PhyView analyzer provides 2 measurements of 10, 100, 1000 base T interface parameters, wideband return loss and wideband crosstalk. These are considered interface measurements because they are not specifically related to transmitters or receivers. Wideband return loss, or echo, is a bulk measure of port under test deviation from ideal 100 ohm impedance match. It is reported in dB, representing the ratio of reflected power to incident power. Ideally, 0 power is reflected, thus producing very negative dB values. IEEE 802.3 requirements generally plot return loss as a function of frequency, with the requirement that return loss remains below minus 16 dB up until 40 MHz, then rolls up to about minus 8 dB at 100 MHz. 802.3 requirements are further complicated by the requirement that the measuring entity ranges from 85 ohms to 115 ohms in order to account for the effects of Category 5 cable characteristic impedance variation. 100 base TX and 1000 base T signals concentrate most of their energy below 40 to 50 MHz, so in practice, the minus 16 dB return loss flat limit line is the most critical region. This limit line can then be adjusted to a more stringent limit of minus 20 or minus 21 dB when making measurements from a nominal 100 ohm instrument in order to account for the plus or minus 15 ohm measuring impedance variation. Hence, the wideband return loss measurement performed by the PhyView analyzer has the potential to sort out well-matched ports from marginal ports and failing ports. The wideband return loss measurement is only made on 1000 base T ports, though its relevance applies to all link rates. It offers a measurement range from minus 26 dB to about minus 8 dB. Measurements can be made on pair 1, 2, 3, and/or 4. As with PSD and SNR, measurements can be performed on multiple test ports simultaneously. Wideband return loss is locally calibrated measurement along the lines of PSD described earlier. Crosstalk, that is, energy leakage between twisted pairs, is specified for 10, 100, 1000 links, but not specifically for 10, 100, 1000 ports, and is therefore not a component in traditional physical layer testing. However, as a member of a link, an Ethernet port can actually contribute to crosstalk through physical mechanisms such as magnetic packaging, circuit traces, and socket characteristics. The wideband crosstalk measurement assesses crosstalk between each of the 6 pair combinations, that is, pair 1 to 2, pair 1 to 3, 1 to 4, 2 to 3, 2 to 4, and pair 3 to 4. It is reported in dB, the ratio between leakage power and transmitted power. Lower negative dB readings mean lower crosstalk. Much like return loss, wideband crosstalk is a bulk reading across all frequencies. The IEEE 802.3 link performance limits specify crosstalk at minus 39 dB up to 20 MHz, then rolling up from there to minus 27 dB at 100 MHz. While higher frequencies conduct more power between pairs, the spectral transmit power at higher frequencies is much lower, meaning a practical wideband limit for crosstalk will be in the minus 36 to minus 37 dB range. Ethernet ports will typically be much better than that unless there is some sort of defect. Like return loss, crosstalk is only measured on 1000 base T connections, though the pair 2 to 3 crosstalk figure is applicable to all links. The meter can range from minus 39 dB to about minus 12 dB and is mainly useful for resolving defective behaviors from viable performance levels. As with PSD, SNR, return loss, measurements can be performed on multiple test ports at the same time. Wideband crosstalk is locally calibrated measurement along the lines of PSD and return loss described earlier. The PhyView analyzer provides 2 measurement types that are utilized in 10, 100, 1000 receiver testing. Link stability is an extension of the link status measurement described earlier. Link stability involves periodic sampling of link status function over a specified count of samples. The link status parameters sampled are link indicate, gigabit remote RX status, and gigabit local RX status. While link indicate, that is, link up or link down, can be sampled at any link rate, gigabit receiver status can only be sampled on 1000 base T links. However, link indicate tends to exhibit technology and device-specific behaviors, while gigabit RX status tends to have more predictable behavior across different technologies and PHY devices. Generally, either can potentially be correlated to packet flow and bit error rate. However, gigabit remote RX indicator tends to correlate much closer to 1000 base T packet errors regardless of the PHY technology deployed in the port under test. This makes it a great asset for assessing port under test receiver performance while under physical impairment. The link stability measurement is best suited for receiver testing with standalone 10, 100, 1000 ports. Each test port also offers a layer 2 frame generator and counting resource. This is beneficial for receiver testing in devices such as Ethernet switches with 2 or more 10, 100, 1000 ports and the ability to bridge layer 2 traffic between those ports. Transmit packet length is programmable, as is packet gap, with maximum packet flows at line rate. Packet flows may be continuous or bursted counts. 4-byte repeating payload patterns can also be configured. On the receiving port, unfiltered layer 2 packet counting and error counting is supported with virtually unlimited count size. External packet analyzers may also be utilized with the PhyView analyzer to take advantage of certain configurable physical layer impairments available in all PhyView test ports. Now that we have introduced receiver measurement capabilities, we'll turn to the broader subject of 10, 100, 1000 base T receiver assessment. While IEEE 802.3 standards are quite specific about transmitter testing, the design and implementation of receiver tests generally does not get much attention. Instead, the standards describe a range of worst-case link characteristics, for example, insertion loss or crosstalk, and then might include a target bit error rate performance. Commercial solutions for 10-100 and 1000 Phi testing do not address receiver tests. The PhyView analyzer combines three types of resources to enable 10-100 1000 base T receiver tests. The first resource is a suite of precise, programmable, inline physical impairments that are available to each test port. These may be used to model worst-case IEEE 802.3 link conditions and to skew those well beyond worst-case conditions for the purpose of performance margining. Impairments include worst-case link insertion loss, ingress noise or alien crosstalk, timing offset, timing jitter, slew rate control, and impedance mismatch. We'll get into greater detail concerning impairments in the next couple of slides. The second resource is the receiver measurement capability described in the previous slide, and the third resource is the local SNR metering described earlier. These resources combine to produce high defect coverage of 10-100 1000 base T receivers with time-efficient and fully automatable methods. Each PhyView analyzer test port includes an electronic filter to model 802.3 worst-case insertion loss. One might think of this as a 100-meter spool of Category 5 cable, though in reality it is a slightly more severe impairment than that, as it produces minus 24 dB attenuation at 100 megahertz. The line loss impairment is matched to 100 ohms and is also designed to exhibit approximately linear phase over frequency, much like a long cable. It may be applied to all four pairs as required for 1000 base T testing, or it may be applied selectively to just the outgoing transmit pair for 10-100 base T testing. This impairment is also available to external packet analyzers that connect through the PhyView test port. A second form of line impairment is active noise insertion. This impairment models the effects of alien crosstalk that naturally occurs in dense cable bundles, crowded wiring closets, and congested cable runs. This noise is random, uncorrelated to data signals, and is spectrally shaped similar to 100 base T. The ingress noise can be programmed over a wide level from minus 6 dB to plus 21.5 dB with granularity of half dB steps. The impairment is calibrated such that 0 dB corresponds to 40 millivolts peak to peak on the outgoing transmission signal from the test port. 40 millivolts is a specified tolerance level for 100 and 1000 base T in IEEE standards. The noise impairment can be applied to all four pairs or can be applied selectively to the outgoing 10-100 base T pairs. Internally, the PhyView analyzer receiver is buffered by 2.7 dB from this impairment, meaning that during 1000 base T testing, the device under test experiences a higher magnitude impairment than the local test receiver. As with the line loss impairment, the ingress noise impairment is available to the external packet analyzers and may be combined with the line loss impairment in order to fully model worst-case IEEE 802.3 and beyond link conditions. When a PhyView analyzer test port is linked to a port under test, the analyzer possesses capability to skew signal timing, to produce randomly jittered signals, and to control slew rate. These impairments are not available to an external packet analyzer. Programmable timing offset models transmitted symbol periodicity. Nominal for 10-100 base T is 125 megasymbols per second, and for 10 base T is 10 megabits per second. The offset impairment can vary this timing to plus or minus 50 ppm, plus or minus 100 ppm, or plus or minus 115 parts per million. These figures both match and exceed worst-case requirements for base T performance. Programmable timing jitter causes transmitted signals from the PhyView test port to randomly modulate so as to model random symbol jitter to a receiver under test. The jitter amplitude can be configured from minus 6 dB to plus 24 dB, where 0 dB corresponds to 1.4 nanosecond peak-to-peak jitter as specified in 10 and 1000 base T specifications. The random jitter is shaped over frequency to meet the jitter channel requirements in 1000 base T. Test ports offer some degree of amplitude and slew rate configuration. Wideband output power may be configured over a 2.1 dB range, while slew rate may be configured between 0.1 and 0.27 volts per nanosecond. This latter capability, when combined with worst-case insertion loss, can be used to produce the highest degree of high-frequency attenuation that a 100 or 1000 base T receiver can possibly experience under the standards. The timing offset impairment, jitter impairment, and slew amplitude control may be layered as additional impairments on top of line loss and amplitude noise ingress impairments described earlier. Finally, each test port can be configured to apply a fixed minus 12 dB impedance mismatch, that is, a mismatch that will produce a minus 12 dB wideband return loss. Now we will introduce the PhyPerformance test suite for the PhyView analyzer. The PhyPerformance test suite is an optional software feature for the PhyView analyzer that provides highly integrated, fully automated 10, 100, 1000 base T port testing and sequencing at a single button press. The suite is comprised of 6 sequenceable tests and 1 special application for DC unbalance analysis in power sourcing equipment. The sequenceable tests include basic capabilities, 100 base T transmitter testing, 1000 base T transmitter and interface testing, and impaired receiver testing for 10 base T, 100 base TX, and 1000 base T. The test suite will automatically adapt to 10, 100, 1000 base T port under test configuration capabilities and maximize test coverage given those capabilities. For example, if a 10, 100, 1000 port supports auto MDI, then transmitter tests will cover both MDI and MDIX for 100 base TX. The test suite can automatically sequence up to 24 ports to a single test report. Users may select both tests and ports to include in a sequence. The standard test report is a colorful and informative pop-up Excel spreadsheet workbook with 1 page per port tested. The report includes color-coded notations and graphics for all tested parameters to rate them as excellent versus marginal versus failing. Another powerful feature of the standard PhyPerformance test suite report is the production of certain critical IEEE 802.3 parameter estimations. Values for 100 base TX and 1000 base T peak-to-peak voltages, droops, rise-fall time, and pulse mask fits are derived and reported on a per-pair tested basis. Cyphos Technologies has worked extensively, including through independent third parties, to analyze and verify the accuracy of these values. Let's take a closer look at PhyPerformance test suite's transmitter and interface tests. These tests provide extensive and fully automated coverage of 100 base TX and 1000 base T transmitters and interface characteristics. They also deliver 802.3 parameter estimates. 100 base TX tests report wideband transmit power, residual distortion, low frequency PSD, wideband PSD, and estimations for peak-to-peak voltage, pulse droop, and rise-fall time. These are reported for MDI and MDIX connections. 1000 base T tests report wideband transmit power, residual distortion, low frequency PSD, wideband PSD, pair timing skew, wideband return loss, wideband crosstalk, and estimations for peak-to-peak voltage, pulse droop, and test signal number 1 mask fit. Graphics colorfully annotate performance using green for excellent, yellow for marginal, and red for problem performance levels. PSD plots color code pairs using TIA-EIA conventions for twisted pair numbers and insulation colors. PSD test limits are also plotted. On the receiver test side, the PhyPerformance test suite offers fully automated tests for 10 base T, 100 base TX, and 1000 base T. Users can select whether to use link stability measurements or packet flow measurements during receiver tests. Link stability is useful in testing standalone or unbridged ports, while packet flow can be used to test Ethernet switch ports that bridge or broadcast layer 2 traffic. All receiver tests incorporate a range of impairments and utilize local test port SNR metering to assure that those impairments do not adversely affect link stability on the test port side of the link. Tests also include logic to support Ethernet switch bridge priming as required for packet flow testing. As with transmitter testing, 10 base T and 100 base T interfaces are tested with both MDI and MDIX connections. Impairments always include worst-case line loss and then combine in varying degrees of alien crosstalk, timing offset, timing jitter according to the link rate. Generally, 100% readings of link stability or packet flow indicate good headroom to the IEEE 802.3 specified performance levels. 1000 base T receivers are tested both in master and slave timing modes with scaled impairments that are appropriate to each of these modes. Local SNR monitoring is especially important for 1000 base T receiver testing since impairments must be applied bidirectionally. For manufacturers of power sourcing equipment, such as PoE switches and midspans, the PhyPerformance Test Suite offers a very unique and powerful test to assess port susceptibility to the phenomenon of DC unbalance. Generally, this is a very challenging measurement, yet one that is vital to the integrity of PoE systems. The application combines PhyView Analyzer test ports with PowerSync Analyzer test ports, a simple configuration that SIFOs can provide in a single PowerSync Analyzer chassis. The DC unbalance application measures and produces plots of SNR, 50 kHz PSD, and estimated droop versus DC unbalance magnitude. Accurate DC unbalance levels from 20 to over 70 milliamps can be created in a manner that does not severely impair local magnetics in the PowerSync Analyzer test port. Reporting is a pop-up Excel spreadsheet with colorful annotations of pairs, limit lines, and limit performance. The PhyView Analyzer software is supported on Microsoft Windows and Linux systems. The two major components to PhyView software are PVA Interactive, a graphical user interface, and PowerShell PSA, a script automation language based on Tcl/Tk. PVA Interactive is an intuitive, easy-to-learn environment. Tab menus are organized by basic resource types, and interactive measurements on one or more pairs are easily performed. The menu also supports an automated port calibration sequencer and PhyPerformance Test Suite described earlier. PowerShell PSA is a powerful scripting language offering intuitive PVA commands and easy interactive debugging from an interpretive command query environment. Custom automation scripts are easily created to fulfill desired tasks. PowerShell PSA offers deeper, more robust access to PhyView Analyzer resources than is available to PVA Interactive. PowerShell PSA is shared by other SIFOS instruments in the PowerSync Analyzer family. The PhyView Analyzer is accompanied by several accessories. Special high-performance RJ45 test cables are provided with every test port. Since test leads are vital to measurements and calibrations, SIFOS provides color-coded cables and connector clips so that users can keep track of which cables are used in each test port. SIFOS offers several optional components with the PhyView Analyzer. The PVA PL4 is a 4-channel wideband loss unit offering 4-channel losses of 1 dB, 2 dB, 4 dB, and 8 dB. This unit can be used as a metrology verification tool since it can produce fixed wideband losses between 1 and 15 dB. Wideband power, PSD, and SNR metering can be assessed with these channels. The PVA LI4 is a 4-channel unit with different line impairments. These include 4-pair minus 14 dB return loss channel, a 4-pair minus 17 dB return loss channel, an IEEE limit line over frequency return loss channel, and a pair group specific crosstalk of minus 32.5 dB and minus 23.4 dB channel. These units are aimed at verifying wideband return loss and crosstalk measurements. Finally, the PVA DCU is used in combination with the DC unbalanced test application described previously and is critical to the process of creating and isolating DC unbalance in combination with the PowerSync analyzer. Let's now revisit the paradigm introduced earlier for 10-100-1000 Phi testing. In comparison to traditional Ethernet Phi testing, the PVA offers the opportunity to radically increase testing samples from single pairs to many or all ports. In addition, the ability to efficiently and effectively test receivers adds an important dimension in test coverage. For those compelled to run the full gamut of IEEE 802.3 tests, results from the PhyView analyzer testing can efficiently point to the ports and pairs that most need more in-depth analysis. While packet flow testing may still play a role in the assessment of Ethernet switch fabric or router forwarding tests, the concept of packet flow testing for physical interface assessment is completely outmoded by the PhyView analyzer. PhyView analyzer measurements provide much deeper insights into physical layer performance with no additional effort and in less time. The PhyView analyzer clearly addresses the 10-100-1000 coverage gap described earlier. By combining true physical layer measurements, high coverage receiver tests, and very high degree of plug-and-play automation, the test paradigm for 10-100-1000 base T is fundamentally altered. Thank you for your attention and interest in the PhyView analyzer from Siphos Technologies. Further information covering the PhyView analyzer is available from our website, www.siphos.com. Feel free to contact Siphos directly or to contact a local distributor of Siphos products should you have further questions. Your local distributor for Siphos may also be found within the Siphos website. Speaking for all of us at Siphos, we look forward to helping you simplify the task of product verification both today and well into the future.